Okay. All right. So we'll start now. So last time we discussed decomposition of polyhedra. We will have a little bit more to say about it today. Then I talked about Redon's theorem, but Redon's theorem was actually an introduction to Tverberg's theorem. Tverberg's theorem is a generalization of Redon's theorem. And in the process of proving Tverberg's theorem, we needed this colorful Caratheodory's theorem. Okay. So our plan today is talk about the decomposition of polyhedra a little bit more. I'll just state some facts. And then we will discuss the colorful Caratheodory theorem. And then we will start the ellipsoid method. So are there any questions from last time? Okay. Yeah, so but please keep asking. So last time we said any polyhedron can be decomposed as a sum of a polytope, that means a convex hull of a finite number of points, and a cone. Yeah. So for example, if this was the polyhedron described by these intersection of these half spaces, then there is a little polytope here, yeah, and then it extends to infinity. The extension to infinity is achieved by this cone, and that is this C here. And this part is the Q in this example. We could, yeah. Now one could ask, is this Q unique and this C is unique? This is what Srijato asked last time. Is this decomposition unique? Okay. Now, and he also pointed out that there are, of course, trivial ways in which it can be made not unique. For example, this was our original polytope. We could have added some stray points outside and declared this to be our Q. And even if we extended this to infinity using the same cone, we would still get the same polytope. So maybe we could ask for the minimal Q, the smallest Q, so that this equation holds, and then maybe this is unique. Okay. Now that, as I had hinted, that may not be true also. And let me give you an example. So look at this polyhedron described just by one inequality. Yeah. So this was a polyhedron. You remember we discussed it some time ago, and I had asked you to describe this polyhedron as a conic combination of rays, yeah, of some generated by a certain number of rays. Yeah. So now if you look at this particular polyhedron, what is this polyhedron? This is the origin, yeah, and this is raised a little bit. Yeah, this line is passing through y equals 1, yeah, and this is the polyhedron that I'm talking about. And now, what is the cone? Well, you shift the same polyhedron to the origin, and that becomes your cone. So our cone in this case is this object, but the polyhedron is this cone shifted up. So this Q in this case is just this singleton point. This point 0, 1 can be thought of as our Q in this case, and the cone is this C, which is the upper half plane. Okay. But you immediately notice that actually there was nothing special about this point. We could have taken this point also. or this point. Yeah, any point on this line. And each of them is a legitimate Q for the same cone. Yeah. I hope that's clear. Yeah. So this minimality trick doesn't settle the matter. Okay. It turns out, however, that the cone is already unique. Okay. Yeah. So there is no, you don't have any flexibility in terms of cones. The cone is always unique. There are situations like this where you may not be able to generate it using a unique, or there's no way to identify a unique polytope which will generate this this polytope. Okay. But yeah, so one can salvage something by a slightly deeper analysis of what is going on. So it turns out that this problem arose because there was an entire linear space, sorry, yeah, an affine space here, which was inside the polyhedron, or in other words, this cone, the cone contained a linear space, a subspace. Yeah, the entire line was there. And it was because of that that uniqueness got into trouble. Okay, last time I gave you the example of a book. Yeah, so if you look at the area between two planes, yeah, the area between two planes may be lifted up, then any point on the spine of the book can serve as your Q. Yeah? So, but if this cone is pointed, yeah, so a cone is pointed, meaning it has something like this. So when do we say that a cone is pointed? If there is no linear space contained in the cone. So this cone is not pointed. Yeah. So if the cone is pointed, then this Q is uniquely determined. Again, one has to be a little careful about how, but this Q will be uniquely determined by once you tell me the polyhedron. Okay, but when the cone is not pointed, then you have trouble. But actually, there is a better decomposition theorem, a more what should I say, fine-grained decomposition theorem. And I want to state that, and then we will continue. So please read this.
Jaykumar, one question. So your polyhedron P is represented by AX less than or equal to B, right?
Correct.
And your cone will always be AX less than or equal to 0, wouldn't it?
I don't think so.
Oh.
One second, I'm getting confused. Maybe you're right. So AX less than equal to 0 is I'll have to think, but yeah. So, but go ahead. Suppose that is the case. I believe that.
So, in a way, isn't it unique in a way?
Sorry, the cone is unique.
So that AX less than or equal to 0 represents some particular cone after all.
Yeah. But I suppose the same polyhedron, can it be described by many system of equations, and then each of them might demand that it has its own cone.
Sure. Thanks.
Yeah. Let me. I will think that through more carefully. Yeah. So, but the theorem that I wanted you to read is this one. Let's see. So every polyhedron has a unique minimal representation of what form? So there is this part which we used to call Q, and then there is a cone, and then there is a linear space.
Sorry to interrupt. if Ax equals to B has a solution, then is one decomposition the following? You let the polytope be just a single point which satisfies Ax 0 equals to B, and your cone is Ax less than equals to 0.
Sorry. So the initial equation
So if
was,
it Ax less than equals to B,
yes.
so I'm just to be clear, if it
Yeah.
has some solution, if the equality system has some solution, say X not equals to B, then is the decomposition the following, that the polytope is just a singleton point x0 and cone is the system of inequalities, say x less than equals to 0.
Yeah. So Ax equals B might have multiple solutions also, right?
Well, you take any one of them. And
So yeah, so I suppose that is correct. So if you take any one of them and then write Ax less than or equal to 0, that will be the second part will be a cone and the first part will be a polytope. Yeah. Ax equals B, yeah, will be just a single point. Yeah. But the general theorem is this, that if you give me any polyhedron, yeah, I'm sorry, any polyhedron, it can be written. So last time we said it would be a convex hull, which this was the Q part and this was the C part. Okay. Now the C part we are further decomposing into basically a pointed cone and the linear space of P. Yeah, by linear space mean all those directions where an infinite line in both directions is there. You just take the span of them. Yeah, that entire affine subspace is sitting inside P. You shift it to the origin and you get the linear, sorry, you get the linear space. And now, so you have this linear space. Look at the orthogonal space to this linear space. And in that, look for the convex hull and the cone there. Okay. So let me draw a little bit. I'll not be able to draw very well. So this is your linear space. And then this is the orthogonal direction. In this direction, you look for a cone and you look for a polytope here. Yeah. And it should be minimal with this property. Then the linear space, this polytope, and this cone together will describe your original polyhedron. Okay. And here some uniqueness holds. What is the linear space is completely determined, which is not hard to see. And then the cone is generated by this. These yi's are unique, but they are not absolutely unique. They are unique up to multiplication by positive constants, because whenever you have a cone which is generated by some rays, if you shrink some ray by a little bit, yeah, it should not matter. Yeah, if you shrink it by or extend it by a constant. So the yi's are determined up to multiplication by a constant, and not only the convex hull, but we know that the convex hull is determined by its vertices. Okay. So then there is uniqueness. So in particular, if this was not there, if the cone itself was pointed, then the cone and the convex hull will be completely determined. Now, this is a more sophisticated theorem. The amount of theory we have done, basically whatever we did so far, we did.
I'm sorry, could you explain what linear space P?
Linear space of P means? Yeah. So, yeah. So we understand what a cone is, right? Cone of P. Yeah. So now look at the largest subspace, meaning a vector subspace, which is contained inside the cone. The cone always contains the origin, right? But sometimes the cone can be like this, in which case this one-dimensional space is there
Okay.
inside the cone. So that subspace is called the linear subspace. In other words, imagine you have a polytope and you are just building an infinite cylinder out of it. Okay. Then what have you done? You have translated that polytope in some direction. Okay. In higher dimensions, you could take the polytope and translate it in some directions. Yeah. Those directions together, they span a space, and that is the linear space.
So if ax less than equals to 0 is the system of inequalities, is this
Sorry,
just a kernel? So if the cone is given by ax less than equals to 0, then
yes.
is linspace be just the kernel of A?
Sorry, then the kernel of A. All those things which yeah. So ax equal to 0. All those things that satisfy ax equal to 0. I think.
Yeah, right. So the kernel of A.
Yeah. Because
okay,
yeah, let us see. So you are absolutely right. So if you write ax less than or equal to b, and suppose there is some direction, let us say x star, and you can extend it in both directions. Yeah, that is any multiple of x star continues to satisfy this equation, whether positive multiple or negative multiple of x star satisfies this equation. Sorry, ax less than or equal to 0, and any positive multiple of or negative multiple of x star continues to satisfy this equation. That means ax star must have been 0. If ax star was not 0, in at least one direction you would have got into trouble. Yeah. Okay. But this is just a geometric picture that is written here. That is, you give me any polyhedron, don't worry how it is defined. I mean, there are many ways. Yeah. So look at that polyhedron object. That object contains a little rounded part at the bottom. Yeah. So like that. Yeah. But this polyhedron could have extended up and down. Yeah. By a linear space. That linear space is gathered here. Then there is the pointed part, this recension cone of this. Yeah, so that cone is written here, and the convex hull, which accounts for the bottom little thing that happens in this polyhedron. So every polyhedron has a little bottom. I mean, of course, it might be top, it might be coming down, but there is this little part which has some faces, and it looks like a finite, nice polytope. And then it is extended to infinity, sometimes only in one direction, and sometimes infinity in both directions. When it is extended to infinity in both directions, that part comes from the linear space. When it is extended to infinity only in one direction, that comes from the cone. Is that okay? So as I was saying, this theorem requires a little more, I mean, work than just the fundamental theorem of linear inequalities. Any questions? I want to return to this thing that we left last time. So the Colourful Caratheodory theorem, I hope, I don't know if you remember it. So you have D+1 sets. Yeah. So these were the various colors. The red points, the blue points, and the green points. Okay. So the red points constitute one set, the blue points constitute one set, the green points constitute another set. We are in 2 dimensions here, but in D dimensions, there are D+1 such sets. And if you take the convex hull of the red points and the convex hull of the blue points and the convex hull of the green points, there is a point which is common to all of them. And the theorem claims that that very point can actually be generated by d+1 points. Now that is plain old Caratheodory's theorem. Yeah, whenever something can be spanned by as a convex combination of some number of points, we don't need all of them. Just d+1 of them. The dimension +1 is always enough. But Colourful Caratheodory's theorem goes one step further. It says that in this situation, you can pick those d+1 points in such a way that one point is red, one point is green, and one point is blue. Yeah. So you will never need to repeat a color. Okay. Yeah. So is the statement clear?
Yes.
Yeah. Okay. So why is this theorem true? Yeah. I mean, this of course contains the Caratheodory's theorem, and you have been assigned the Caratheodory theorem in your homework. But please don't invoke the Colourful Caratheodory theorem and say that, by the Colourful Caratheodory theorem, the Caratheodory theorem is true. Okay, you need to prove it directly, and it has a much simpler proof, and I'll have more to say about it. Okay. Okay, so here's how we prove the Colourful Caratheodory theorem. So here is this point y, which is the same picture. I just copied it. Yeah. So this point happens to be in these three convex hulls. In all of these convex hulls, it is there. Yeah. So now we would like to show that this point is a convex combination of some colorful set. Yeah. So we'll call this a colorful convex combination. By a colorful convex combination, I mean you have to pick d+1 points, one from each color. Yeah. So we want to show that this X can be written as a colorful can be expressed using a colorful convex combination. So now maybe it cannot be. Yeah. So let's assume it cannot be, and let us look for all colorful combinations. So you look at 1 point here, 1 point here, 1 point here, and 1 point here, and see all the points that you can produce. And similarly, and all those points you can produce. So look at that space of all those points that you can produce by taking d+1 points, one of each color. And somehow your X is outside of that set. Okay. Now, by plain old Caratheodory's theorem, among the red points, if we want to express X, we need only d+1 of them. So we can throw away all the red points. Let us assume that the total number of red points is only d+1. At most d+1, the number of green points is at most d+1, the number of blue points is at most d+1. So the situation is all finite, even though I have drawn patches here. You shouldn't take those patches seriously. There are d+1 points of each color, and they generate X, and we would like to get a colorful combination for X. Assume that there is no such colorful combination for X. What is the closest point? Yeah. There are finite number of possibilities, finite number of colorful combinations that you can take. What is the closest point, yeah, that you can realize using such a colorful combination? Yeah. Now, I'll let you think about why this closest should exist. One part I have simplified. I have said there are only finitely many combinations. But even if I fix a blue point, fix a red point and a green point, these are the various convex combinations that can be generated by that choice. Among them, there is the closest point, that point closest to X. Okay. And then you can imagine that there are only finitely many possibilities, and among them you will get the closest. Okay. So never mind. Let us assume that Y is the colorful combination, yeah, in this system, which is closest to X. And we will get a contradiction by showing that there is an even closer point. Is this clear? Is the problem clear? Is the idea clear? The approach? Yeah. So here was your point X, and here is this point Y, which is claiming to be the closest point to X. That is the closest point which can be generated as a colorful combination. Look at, so uses all the colors to generate this point, at most one of each color.
Sorry, how do you know such a maximum exists?
Such a minimum exists. That's what I was trying to say. That first, once you pick a point of each color, a pink point, a green point, and a blue point, that defines a convex hull. Okay, and if X is outside that convex hull, if X is in that convex hull, X is a colorful combination. If X is outside, there is a closest point to that convex hull. For each choice of a red point, green point, and a blue point, in the convex hull of those points, there is a closest point to X. So there is only a finite number of such convex hulls. Each of them has a unique minimum. Yeah, and you take the minimum among those minima. Yeah, and you will get the unique point one. Is this clear? Srijata?
Yes.
Yeah. Okay. Yeah, but I will let you think about it. Okay, so let's assume that there is such a Y, and we are going to claim that that there is a contradiction. So now let us just So this Y is a convex combination of some colorful set of points. Okay, maybe some are in this side, some are. Now, take this X, take this Y, and draw the line which is perpendicular to this line. Yeah? So this is a affine plane which is perpendicular to this. Yeah? Now, the point is, can there be any point which generates Y which is on this side? So there are many points that generate this colorful combination. There is a colorful combination which generates Y. Among them, suppose there is an orange point. Yeah. Among them, this orange point was not here, but was on this side. So suppose this orange point was here. Well, so that means Y is a colorful combination, and the orange contribution is being provided from here. Okay. Now, suppose I increase the weightage of the orange combination, then this point will start moving in this direction. Yeah, it will be in the line joining Y and this orange point. But then if you move a small enough amount, you will actually be closer to X than before. And that would be a contradiction. Is this clear? So Y is now a colorful combination. My claim is no point in this colorful set, which is generating Y as a convex combination, actually is on this side of the hyperplane. Everybody agrees? Want me to repeat?
Okay, I get the idea.
Sorry?
I get the idea. So this is similar to proof of the separation theorem.
There are analytic proofs of separation theorem which
where you take the closest point and it satisfies.
Yeah, but let us see, there are some. So right now, if you look at the sphere with center X and this as radius, that sphere is tangential to this plane. Yeah. If you move in this direction, you are stepping into the sphere. If you are stepping into the sphere, you are closer to X than Y. Okay. So no point which generates Y can be on this side of this hyperplane. Okay. This colorful set. Yeah. Can some point be on this side? Maybe this orange point, instead of being on this side, it's actually on this side. But you see, if Y is a convex combination of some points, and if there is any point which is strictly to the right, then there, to balance it out, there must be a point also to the strictly to the left. Yeah. For example, suppose you put your coordinate plane like this. Now the convex combination of all these points is Y. So if this is giving you a positive contribution, If this point is giving you a positive contribution, there must be some point which is giving you a negative contribution for this point to lie on this hyperplane. Okay. So what have we concluded? If y is the closest to x and y is a colorful combination, then every point that contributes to y, that is in the convex combination, it has a positive weight. Yeah. That should, those points should all lie on this hyperplane itself. Yeah. So something is happening. When y is generated as a colorful combination, all the points that generate y have to sit on the hyperplane. Is this clear?
Sorry, could you repeat why no color can be to the left of the hyperplane?
Sorry, why no color could be on which side?
So why one of the generating points, that why can't it be to the left of this hyperplane?
Why it can't be to the left of this hyperplane? On this side, that is right.
Yes.
Yeah, we are both thinking of left in the same way. Okay, this side. Yeah. So suppose there was this orange point was not here, but was on this side.
Yes.
Yeah. Now, so this orange here was not there. Huh? This was not there. Now, this orange has a certain weightage. Yeah. So if I increase the weightage for this orange,
okay.
the point will start moving in this direction.
Right.
And then it will be closer to x than before. Yeah. Maybe y is here, the orange point is here. Then if I move, then if I drop the perpendicular on that line, that will be the closest, and that will be closer than this hyperplane. Yeah, closer than this. Yeah, you can check. Okay. So it can't be on this side, it can't be on that side. So all the points that generate y are living on this hyperplane. Is this clear? Yeah. Okay. Now, we were in which dimension? We were in RD. So what is the dimension of this? I say hyperplane, but I mean this affine plane. What is the dimension of this space? Of
D
this?
minus 1.
It is D minus 1. And this point is a convex combination of some points in this D minus 1 dimensional space. Now, in D minus 1 dimensional space, what does the standard Caratheodory tell us? If any point is generated as a convex combination, how many points do you need to generate it?
D plus 1. Sorry, D.
D.
Yes.
That means even though you have generated it using D plus 1 points sitting on this hyperplane, we actually needed only D of them. That means one color, let us say the green color, was not needed. That means this very y can be expressed using some colors, but this green is not needed. You can generate it out of the rest. Is that clear? Because you are inside this D minus 1 dimensional space. Okay. So fix that. So this y can be generated using everything, and there is no weightage on this dark green. There is no weightage on this dark green. But this point x was a convex combination of dark green points. It was in the hull generated by the dark green points. That means there must be at least one dark green point on this side. So now we have generated this y as a convex combination of points other than this dark green. Okay. And there is a dark green on the left. So you take this y and add a little bit of this dark green point so that this y starts moving in, and which is again a contradiction for the same reason. Once again, we have established that this y is a convex combination of just D points, which means one of the colors is available to us. The question is there a representative from that color on this side? Well, your point x is on this side, and x is in the convex hull of the green points. So one of the green points has to be here. If all the green points were on this side, then their convex hull would also have been on that side. Okay. So there is at least one green point, maybe here, maybe here. but that means that it is possible for you to move in that direction, and it will still be a colorful combination, because the old combination did not use dark green. Yeah. And then we are just adding a little bit of weight to the dark green, which was not used previously. So totally, it now still is a colorful combination. No color is being used. No 2 points are not being used for any color. And we are moved closer to X, and that's a contradiction. End of proof. Yeah. So if you
so the contradiction is that X not equals to Y cannot be true.
That's right. So how did we start? Suppose X cannot be expressed as a colorful combination. Let Y be the closest point. So the only assumption we made was that X cannot be expressed. Hence, it must be the case that this Y must have been here itself, or there is a contradiction. So the assumption must be false. That means X can be expressed. Is this okay?
Yes.
Yeah. Notice that we used Caratheodory's theorem in the proof of colorful Caratheodory. Okay. So when you do your homework, yeah, it would not be fair for you to invoke colorful Caratheodory to prove Caratheodory. Yeah. So now I said I want to make a remark. See, when you are given a convex combination, that is, a point has been expressed as a convex combination in some d-dimensional space, and we know by Caratheodory's theorem that there is a convex combination which is supported on at most d+1 points, which generates that. And finding that d+1 size set whose convex combination leads to this point can be solved algorithmically. Okay. So in fact, if you look at your homework, you will see how to produce those d+1 points. Okay. Now, the same algorithmic question can be asked in this case. That is, somebody has given you green points, d+1 green points, d+1 red points, d+1 blue points. And in each case, they have shown you how X can be expressed as a convex combination of points of that same color. Now they ask you to find a colorful convex combination. Express X as a colorful combination. Yeah. So is there a polynomial time algorithm which will find out which colorful combination produces X? And it is not known. Okay. So I was looking this up on the internet. There seems to be some paper recently, 2016 or 18. Yeah. And so this might be something for you to look at.
So, Jacob, how old is this theorem, colorful Caratheodory?
Might be, I don't know, maybe 25 to 30. I should look it up. 1 second. I have the book here.
So not known by that, it means you NP hard, or even that is also not?
No, it's not known to be NP hard either.
Okay.
So it is not known to be NP hard, and it's sorry, I have the wrong book with me. Yeah, so I'll let you know.
No
yeah.
problem.
See, Tverberg's theorem itself is from the 1960s, but the original proof of Tverberg's theorem was not using this method. Yeah. Then around the early 90s, perhaps, Tverberg's theorem started being proved using colorful Caratheodory's theorem. So I believe, I mean, it must have been sometimes in the 1980s, but I'm not sure. Okay. And there are, yeah. Okay. So I want to talk about the ellipsoid method. I'm sorry, I've been speaking a lot. And is this okay? Is everything clear so far? Yeah. And
Yes.
if you also, yeah, if you have suggestions about the course, you know, this is an online course, and I don't know to what extent I'm able to get through to you. Okay. So if you have suggestions about what I should do, maybe this idea of writing everything before I come to class is annoying. I should do everything, you know, I should write everything in front of you. Maybe that will give you more time. but I make so many mistakes that that will probably be more annoying. But never mind. Okay. So anyway, so please send your suggestions if you have anything. Yeah. In any case, I think both Kavita and I are available. You can just stop by and ask if something is not clear. Okay, so today we are going to start discussing the ellipsoid method. So we have about 45 minutes, which is about what I have prepared for. Okay. So now, if you want to find an optimum, the optimal solution to this LP, you can set up another LP which mixes the dual and the primal. Okay. Did I write this wrong? This was the maximization problem. This fine. Okay. So we know already that the optimum of the primal is always less than, any solution to the primal is less than or equal to every solution to the dual. But if we find even one solution where the inequality holds in the other direction, then we would have found a point where the primal and the dual are actually equal. Okay. So what we do is we have been given this primal LP, we constructed dual. Yeah, this is the dual, and then we equate their objective values. It might have been more honest to just put equality here. Okay, but we know that one side always holds, so that's why we said this. Okay. Yeah. So now, if you get a feasible solution to this LP, then we have found optimal solution. Okay. So, which means testing for feasibility of for a system of linear inequalities is all we care about. This remark we made earlier also. Okay. Now, also, suppose somebody is able to tell us whether a system of inequalities is feasible or not. That is enough also to find a solution. Okay. So this is the second remark. So suppose we know that every system of linear inequalities can be turned into one of this kind, where we have put slack variables and turned everything into equalities, and we did some maneuver so that the only inequalities we have are of this form. Now, suppose somebody has the ability, when presented with such a system, they can tell you whether it is feasible or not. They're just going to give you a yes, no answer. You give them a system like this, they are going to say yes or no. Okay. So now what do? You start with this system and drop the last variable, xn. You remove xn, the column of xn from this matrix, and you ask, is this system still feasible? Okay. If they say yes, now you drop xn minus 1. Yeah. And if they say no, xn can't be dropped, you nevertheless ask, can you drop xn minus 1 and is it still feasible? Okay. So at some point, they will, you will have some variables which are absolutely essential. Okay. Yeah. And now this system will have a unique solution, because if there were two solutions, then you can combine, you can take one solution, subtract it from the other solution, and make one more component 0. Okay. Yeah. So since none of these variables can be dropped, it means that the system has a unique solution. And if there is a unique solution to a system of equalities, just by Gaussian elimination, we can solve it. Okay, so I'm just letting it be vague like this. So if somebody is able to just tell you whether the system is feasible or not, you will be able to use that oracle, yeah, that subroutine repeatedly to arrive at the solution.
Sorry, I just one question. You just said use Gaussian elimination to check whether or not this is slow, but that itself takes order in cube time, right? Isn't that slower than the rest of the algorithm?
No, we don't know how long simplex takes. We are trying to solve linear programming.
Okay, so in cube is just fine.
Yeah, n cube is fine. Yeah.
Okay.
Okay, I mean, we are just trying to get a polynomial time algorithm, and we are wondering if somebody is able to design a system, a subroutine, which given a system of inequalities is only able to say yes or no. Is it feasible or not feasible? How powerful is this subroutine? And the remark we are making is that if you have such a subroutine, yeah, you can in fact find the point which satisfies those inequalities, and yeah, finding a point which satisfies the inequalities is equivalent to solving the linear problem. Okay, so now, so what we are going to discuss today is a new method for solving linear programs, and this is called the ellipsoid method. So I would like to tell you what an ellipsoid is first, and then we will see how the algorithm works. Okay. So now we are in n-dimensional Euclidean space, Rn, and we are here is the ball which is centered at 0. This 0 is the middle of the ball, and it has radius 1. So it is all those points x in this n-dimensional space which satisfy this inequality. Yeah, so this is the ball. Okay. And in matrix language, you will write it as this. Okay. So this is a ball. Now, what is an ellipsoid? An ellipsoid is just a deformation. So you take your space, apply a linear transformation. So this was your original basis. When you deform the basis, you probably get some basis like this. So what was a nice circle might become stretched in some direction, and objects like that are called ellipsoids. So let A be a non-singular matrix, yeah, and C be some point in R. So now consider this transformation. So you take X, apply AX to it, and translate it by C. Okay. So in particular, the point 0 will be moved to the point C. Now let us ask what the action of this transformation does to this this ball. Okay. So first of all, this ball had a center which we assumed was 0. Yeah. So that center will now be moved to the point C. And now this linear transformation might stretch this ball in some funny way, and what you get can be written like this. So we are looking at all those points y, yeah, such that ax plus, so y is of the form ax plus c, where x comes, what did I write? I'm sorry. X sorry, this was meant to be x there. So take a point in the ball and apply this affine transformation to it. That is, you apply a linear transformation and shift it. Okay. So that means, so we can express the ellipsoid in this form. Here we have added this extra variable x. We can eliminate x. Yeah. So we write x as A inverse y minus c. Yeah. And now you substitute this value for x here. So for x, what do we substitute? A inverse
X minus y minus c.
Y minus c. I don't know what. Yeah, that's why I write everything in advance. Yeah. So A inverse y minus c. So now if you substitute here, you will get. So now x, we don't kind of have this extra variable x in our description, nothing wrong. But now we are writing everything purely in terms of y. So y must satisfy this inequality. Okay, so first of all, it is quadratic. Yeah, it's not usual linear. Yeah, it's quadratic. And what you have here is a matrix multiplied by its transpose on the left. Okay. And these matrices are obviously symmetric, because if you take the transpose of this matrix, again, you will get the same thing. Yeah. And these matrices are positive definite because A is non-singular. Now, in your linear algebra course, I assume you have been told what a positive definite matrix is. Also in your algorithms course, you have discussed it briefly. But the point is that if you look at this matrix, we will soon be calling it D. Yeah. So if you look at this matrix, and here's a matrix D, yeah, which is some matrix transpose and then the matrix itself. Yeah. So A inverse I call B. So D is now written, this matrix D here, this matrix here, I'm calling it D, and it is of this form. Now, if you multiply it by X on both sides, yeah. So let us say I multiplied by X transpose on this side and X on this side. It is the same as multiplying by X transpose and X. That means you got a BX and the transpose of BX, which means you are taking a dot product of this vector BX with itself, a dot product of BX with itself. Now, if X is non-zero and this B, yeah, is a non-singular matrix. So if A is non-singular, A inverse is non-singular. So B is a non-singular matrix. So BX is a non-zero vector. And if you take a dot product of a non-zero vector with itself, it can never be zero. It will actually be a positive number. And that is what it is meant to say that the matrix is positive definite. That is, it's a symmetric matrix. And for every vector, every non-zero vector, if you multiply it on both sides in this fashion, what you will get will be a positive quantity. In particular, this matrix has no zero, yeah, eigenvalue. If yeah, if yeah. So yeah, so the object that arises by applying this linear transformation and shifting is called an ellipsoid. Okay. And now here are some facts about positive definite matrices. So if a matrix is positive definite, then it can be written always in this form. In our case, it arose out of a linear transformation, but any positive definite matrix arises out of a non-singular linear transformation in this form. And we just verified that if a positive definite matrix is defined like this, then if you have a sorry, this is again wrong. This should have been not equal. So if you take any X which is not equal to 0, then this is 0. So the net result is that this will be our official definition of an ellipsoid. You can think of ellipsoid as a linear transformation of a sphere. You had a sphere, you just stretched some axis. Now it turns out that, okay, I will give you an example very soon. So let me see. So what is an ellipsoid? Ellipsoid centered at C and defined by this positive definite matrix D is all those points X which satisfy this inequality. Notice that I've written D inverse here. Yeah. So this matrix, yeah, is we will call it D inverse, not D. I made a mistake just now. This matrix will be called D inverse. There is a reason for that. I'll tell you very soon. Okay. Is this clear? So is the notion of an ellipsoid clear? Yeah.
Yes. Yes.
Yeah. You can think about it in two ways, either as a non-singular linear transformation of the honest unit ball, okay? Or you can say that there is some positive definite matrix, yeah, here, which we call D inverse, and then X minus all those points X such that X minus C transpose d inverse x minus c is less than or equal to 1. This x used to be the y when we did the discussion earlier. Now it turns out that whenever you have a positive definite matrix, it has an orthonormal basis of eigenvectors and all its eigenvalues are positive. Okay, so typically instead of calling the eigenvalues lambda, we will call them lambda squared. Okay. Yeah. So the eigenvalues of d will be called lambda squared. Okay. So now let me just tell you what happens. So if let's look at some examples. So suppose this was your d, and with this d, you are trying to understand what ellipse arises with this d. Let us choose this c to be 0. Yeah. So if I chose this d, c to be 0, what is the ellipse that will arise? What will the ellipse in this case? In general, if you had such a matrix with n entries, then it will be an n-dimensional ellipsoid. So right now we are just talking about an ellipse. Yeah. Okay. So now, what if this is d? What is d inverse? What is the action of d? It is scaling the first vector by a factor.
Half comma 1 by 4.
Yeah, so it would be half, 1/4, 0, 0. Yeah, you just take the inverse of the diagonals. Yeah, if these are 0. Yeah, so that is d inverse. And if you ask, in this direction, what is the largest vector so that d inverse x transpose x is less than or equal to 1? And the answer is that, in this direction, it is this number 4. And in this direction, the number is 2. So what the diagonals of the d that arises in this, they are actually the half the lengths of these major axis and minor axis of the ellipse. Okay. Now, if you take this as your d, the two eigenvectors in this case are this. They are also orthogonal. Okay. Yeah. And it is actually this very same ellipse which has been rotated by 45 degrees. Okay. So in this direction, it will be 4, and in this direction, it will be 2. Okay. So if you take this matrix, you write it in the diagonal form, look at its eigenvectors. The eigenvectors, the eigenvalues, I'm making a mistake. Obviously, I'm making a mistake. So, yeah, so these numbers are all, what did I do? Okay, so let me just tell you, I have made a mistake. These are, you have to take the square root of these numbers. Should we do it again? Yeah. See, so suppose you ask for, so d inverse is half 1/4. And now you are multiplying it x1, x2. And we are setting this to be less than 0. All those points x1, x2, which satisfy, yeah, this is our ellipse. Okay. Now set x1 to 0, set x2 to 0. How big can you make x1 so that this inequality is still satisfied? x2 has been set to 0. How big can you make x1 so that this inequality is still satisfied? I'm asking you.
So half.
Sorry, how big can I make x1 so that this inequality is still satisfied?
2.
Well, if you make 2, then you get 4 times half and you get 2.
Oh, yes.
Sorry, what's the answer? How big can you make x1 and still satisfy this inequality? You said x2 has been set to 0.
This is just x1 by 2, right?
No, it is x1 squared by 2. So this equation looks like,
Okay.
sorry, this equation actually looks like x1 squared by 2
Yes,
plus
square root.
x2 squared by 4 is less than or equal to 1.
Yes, square root 2.
Yeah, so that was the mistake I made in my hurry. So, yeah, I'll correct this in the notes. So this are wrong. This should be square root 2 and this should be 2. Okay, never mind. If you have a diagonal matrix, yeah, which is defining an ellipsoid, look at the eigenvalues. They are all positive numbers. Take the square root of those eigenvalues, and those determine the length of half the axis, half axis. So the various axes, their lengths are related to the square root of the eigenvalues. Okay. I'm very sorry. Yeah, I messed this up. But is it clear? Okay. So, yeah. So now, in the remaining 20 minutes, I want to tell you about the ellipsoid method and how it works. So we are going to make some assumptions, and the assumption is that the polyhedron is full dimensional. Okay, I mean, it's not a very easy assumption. Yeah, so we are making some assumptions. So the polyhedron is not sitting on any hyperplane. Yeah, it is a full dimensional fat object. Yeah, and any calculations that we are going to do, we can do precisely. Meaning, so we are not working with finite precision. We are not working with binary numbers. We are actually working with numbers and things like square root 2 and square root 7 and 16th root of something. They can all be computed precisely. Okay. Later on, when next time, these assumptions need to be removed because we don't want to have a truly polynomial time algorithm. That means the algorithm better be polynomial time in the lengths of the representations of all the numbers. Okay, and for that one needs to work harder. But today, just the general principle of ellipsoid method. Yeah, let us assume that these two assumptions work. And now, so we have been given this system. Let us look at this matrix where A is the original matrix and you have stuck B here. And let phi be the maximum size in bits. Yeah. Okay. So I have not written this sentence fully. The maximum size of a scalar that appears in this matrix. By size, I mean its binary representation. And let us just add 1 to the binary representation. Yeah. So that 0, etc. don't get messed up. Yeah. So it's roughly how many bits, approximately how many bits do you need? Yeah. And this is the maximum size actually of any row of this matrix or something like that. And I'm just going to set this number nu to be 4n squared times phi, where A is, let's say, an n, we are in some n-dimensional space. Yeah. So is this clear? Yeah. Now, because of this assumption, using arguments similar to your first homework, yeah, because points, when you do Gaussian elimination, the points that arise, they turn out, they are related to the determinant of some submatrices. These are just remarks which you can verify later. Okay, so it turns out that this number nu is some sort of a bound on any vertex, the size of any vertex. Okay, that means the number of bits needed to describe any vertex, meaning all its components all the total number of bits that are needed put together will fit into these many bits. Okay. So this is just a routine calculation using determinant in your previous are at most 2 to the new, because they can be written in new bits. The numbers that arise are at most 2 to the new. Yeah. Now I'm getting a message here that my internet is not working properly. Can you still hear me? Yeah.
Yes.
Oh, yes.
Yeah. Okay. So we are assuming that our polytope is bounded, and the numbers that were used in describing the polytope were small. And since every vertex is just an intersection, yeah, where some equations are tight, yeah, you can imagine. So when you solve those equations, you will never get something which is outrageously big, because Kramer's rule will tell us that the numerator and denominator are determinants built out of data that was originally quite small. Okay. So these vertices are all fit in new bits. And since the vertices all fit in new bits, the entire polytope is inside, no vertex is farther than r away from the origin. So they all sit in this spot. So what have we got? We have some polytope, and that polytope sits inside a sphere. The sphere has reasonable size, in the sense that its radius can be written in polynomial number of bits. Okay. For the rest, please don't worry too much about these. We seem to be getting very hacky with binary representations, but let us just in the next 5 minutes understand the principle of Kachin's ellipsoid method. Okay. So the idea is the following. Initially, we have already been given an ellipsoid which contains the polytope. We will successively build more and more ellipsoids which will all contain this polytope. Okay. So we will, in Kachin's method, we will go through a sequence of ellipsoids. And how will each ellipsoid be described? For each ellipsoid, you will have to tell me what its center is and what the corresponding positive definite matrix is. Okay. Today we will not worry about how many bits are needed to describe the entries of this positive definite matrix. This is an issue. Okay. And that's why ellipsoid is slightly, technical. Yeah. But the principle is very simple. We will go through a sequence of ellipsoids. The initial ellipsoid was already given to us. And for the initial ellipsoid, the center was given to be 0, which is this center, and the radius. Yeah. So for a unit sphere, this is the matrix, the positive definite matrix. And now we are not talking about a unit ball. We are talking about, sorry, I keep saying sphere, I mean ball. Yeah, that means it contains everything inside. Yeah. So since it's of radius r, remember this time we should ask, we put squares so that when we take square root, we get r back. Yeah. Okay. Good. So this is the situation. Now, how do we?
P need not be bounded, right?
Which, sorry?
Polyhedron? Oh, it's bounded. Sorry. I'm sorry.
Yeah, no, sorry, this is an assumption. Yeah.
Sure.
Yeah. So it is bounded somewhere, and once it is bounded from the matrix, we can determine a reasonable upper bound for the vertices. We build a ball and we are ready with the first ellipsoid, which happens to be a ball. Then what do? We look at the center of, in the ith iteration, look at the center of the current ellipsoid and ask, is this center already a feasible solution? Because our goal is just to find a feasible solution. Because we know that once we know how to find feasible solutions, we can do everything. Okay, that was the point of the first 2 remarks that I made about ellipsoid method. So we ask, is this point a feasible solution? And if it is feasible, we found our feasible solution and we stop. Now, if it is not feasible, then anybody who is complaining is duty bound to give us some inequality out of this, some row of this which is violated. Let it be this one. Okay. So what is happening? Here was your bounded polytope, yeah? And there was this equation which perhaps was defining, yeah, this half space which was defining this polytope, and somehow your point Z is outside, your current center of your ellipsoid is outside. So what you do is you take the same normal vector, but consider this line and consider this half space. Okay, so let me read out what I wrote. So if Zi is not in the polytope, then it violates an inequality of this form. So locate such an inequality. Yeah, somebody tells us this inequality. Then consider the old ellipsoid and this. So I'm not considering, I'm not considering this part. I'm being a little generous. I'm putting that hyperplane through the center and looking at this. Yeah. So the thing that I'm considering is this half ellipsoid. Is this clear? So we started with an ellipsoid, we presented its center, and we said, is this a feasible solution? It was not a feasible solution. So we took this half ellipsoid. Yeah. And now we put another ellipsoid which contains this half ellipsoid. Take the smallest ellipsoid that contains this half ellipsoid. In my case, actually, this is actually an ellipsoid. It almost looks like a circle, but I tried to draw something. So this dotted line here was the old ellipsoid. And the next ellipsoid, the new ellipsoid EI plus 1, is the ellipsoid which contains this half ellipsoid. And since it contains this half ellipsoid, it also contains the polytope. And this new ellipsoid has a center. And that point is called Zi plus 1. Yeah. Yeah. So the next ellipsoid center will be called Zi plus 1. In my picture, it happens to be feasible, but it could have been outside. Yeah. We don't know. Okay. And we repeat. So now we've got an honest ellipsoid again. We take its center. We ask, is it feasible? If it is not feasible, somebody presents us a way of separating the new center from the polytope. We shift that hyperplane so that it passes through this. We cut this part and build another ellipsoid, which will contain this half. And repeat.
So when you find the smallest ellipsoid containing this half ellipsoid,
yeah,
it has some points that are outside the hyperplane, right?
Yes, even these points. Yeah, so that is the thing.
So,
yeah.
So
yeah,
if your center happens to be one of them, then you'll get that the same hyperplane is violated again.
No, the center will move in this direction. I mean,
okay.
Yeah, because with this as center, the old ellipsoid itself was good. Okay, and the smallest ellipsoid will actually have its center in this direction. Actually, yeah, it will be on this side. And we will see soon. Yeah, we will see soon. So there are two claims. One is that this looks like a very awkward object to understand, but it turns out that it can be analyzed. And the volume of the new ellipsoid as compared to the volume of the original ellipsoid is significantly small. Now, don't be carried away by my use of the word significant. It looks like 1 minus 1 over 2n. Okay, so the new ellipsoid is a factor slightly smaller, but hardly smaller. Right? It is like 1 minus 1 over 2n. Yeah. So for every 2n steps of the ellipsoid method, we are shrinking the volume by a factor 2. And one can really complain because the moment this hyperplane was given, I had actually cut down the volume by a factor 2. Yeah, this ellipsoid, this half ellipsoid was a half ellipsoid. It was half of this ellipsoid. But since I want to live in the nice world of ellipsoids, this half ellipsoid I approximate using this ellipsoid, and in the process, I add a lot of junk, and some of it, as Srijato points out, on the other side. Yeah, I live with it, but the point is that I have a nice object like ellipsoid going for me, and I make some dent in the volume. Yeah, 1 minus 1 over 2n. And if I run this a polynomial number of times, it will turn out that the volume will become so small that it will have to be inside the polytope. So this is one claim. The second claim is that if you have a polytope and all its vertices have reasonable size, then its volume will have to be at least 2 to the minus n. Okay, so it cannot have an arbitrarily tiny volume. Okay, if you have a full dimensional polytope built out of a matrix whose coefficients were not too big, then that polytope will be pretty solid. It will have some volume. It's a very small number, exponentially small, but it's not smaller than this, is the point. Then we can estimate how many iterations we need. So I've, with hindsight, guessed. So look at this n. N is 16, n squared, which is the dimension of the space that we are living in. And this is the size of the coefficients. If you run the ellipsoid method, these many steps, what happens? The final ellipsoid that you get will have this volume where each time you are suffering this factor. Okay, so each time you are suffering this factor, initial ellipsoid was entirely contained in a box of dimension 2r. It was actually a ball, but it was contained in a box of dimension 2r. So the volume of the initial ellipsoid was at most, initial ball actually, was at most this much. But the final polytope, I mean, the polytope itself is always contained in all the ellipsoids, and its volume, this claim says, is at least this much. Which means, so let us look at this number. Now we had an estimate for this R, so it was 2 to the nu was an upper bound on R. You might remember somewhere. There was R was 2 to the nu. So we have this inequality. Now it turns out that if you solve this with this value, this number actually turns out to be less than or equal to this. And this is a strict inequality. And we get a contradiction. I mean, I'm saying it in a very ugly way. The point is that if you keep doing this long enough, you will be indefinitely shrinking your ellipsoid. It will shrink to such a value that it cannot even contain the polytope. That means what? At some point, you must not have been allowed to make the Kachin iteration. That is to say, at that point, the center would already have been a feasible point, and nobody would have been able to provide you that hyperplane, which allows you to go from an ellipsoid to a half ellipsoid. Okay. So if you run these many steps of Kachin iteration, you are sure to find a point which is inside the polytope. So claim 1 and claim 2 show this. Is this okay?
Yes.
So please ask.
So you're saying that if the polytope has one visible point, its volume must be at least something.
Its volume must be at least something because it's a full dimensional polytope. We'll prove these two claims now. At least let me just try to prove claim 2. And depending on the time and your patience, I might prove claim 1. So this is a beautiful fact. Your matrix used only small numbers. Using small numbers, you produced some hyperplanes, half spaces, and you produced a solid object which was an intersection of those half spaces. Could you produce a very tiny full dimensional object out of this? The answer is no. It will have significant volume. And since it has significant volume, ellipsoid method, which is coming from outside, at some point will be forced to step inside that volume. The center will be forced to step inside that volume. And then we would have found the feasible point. Now, so suppose it is a full dimensional space. That means if the polytope is not contained in any single affine plane. Yeah. So that means in n dimensions, it must contain n+1 affinely independent points. If there were only n points, yeah, then so these there inside the polytope, you should be able to find. So for example, if it was not a line in 2 dimensions, if it was not a line and it was a solid, then it must contain a triangle. Yeah, so it must contain a triangle. So there must be these 3 vertices which are not all on the same plane. Okay, so let us identify those points. So there are n+1 points which are affinely independent. Now let us consider even the volume of the convex hull of these points. Okay, the claim is that the volume of the convex hull of these points already is significant. Anyway, I mean, this could have been the polytope for all you know. Okay, so the convex hull of these will have reasonable volume. And I will explain if you want. So it turns out that the volume of a convex hull of x0 to xn is actually this number. If you're not familiar with it, I will explain, or you can start thinking and you can tell me why it is true. Yeah. So you take each of these points. So this is n, and each xi is a vector of length n. Yeah. Stick a 1 in the first. Yeah. First column. The first what's it called? Row. Now this becomes an n+1 cross n+1 square matrix. Take its determinant. Take the absolute value and divide by n factorial. Okay. This volume is this is an equality. Okay, so one should be able to just see why it is. Yeah. So this equality holds, but let us just see this n factorial. So how small can this be? Well, n factorial is at most n to the power n. So this factor gives you a hit of n to the power minus n. Now, each of these numbers that arise here we know. So let us look at the denominator. Yeah, let us look at the denominator of any number that arises here. Since we know that these numbers don't use more than new bits, the denominators that arise in the scalars here is at most 2 to the power minus nu. And if you take any determinant, yeah, the denominator that will arise will be a product of the denominators of some numbers. So your definition of determinant is you go through all n factorial things. We are focusing on the denominator. How big can the denominator get? In any such product, yeah, the denominator can never become more than 2 to the n nu. There might have been n factorial terms or something like that. Yeah. So you can always write this determinant with a denominator no bigger than this, and then you will have to divide by this number 1 over n factorial. So that is this number, and this for this n to the power minus n, I have put a factor 2 here, and it is bounded by 2 to the minus 2 and nu. I should have written 2n nu. Yeah, I wrote 2. Is this clear?
Yes.
And you will be able to figure out why this is true. The point is, yeah, I'm out of time. Let me just say how you are probably used to the fact that the determinant, the absolute value of the determinant is the volume of the parallelepiped. Yeah.
Yes.
This is just Gram-Schmidt orthonormalization if you do. Yes, orthogonalization. You will see that it is parallelepiped. But let me just explain. Maybe 1 minute and then I will stop. I will not prove claim 1 today. Yeah. So suppose here are two vectors and we are trying to compute the volume of the convex hull, but consider the parallelepiped here. Yeah. In this case, a parallelogram. So if you can compute the volume of this parallelogram, then half of it is the volume of the convex hull. Okay. In 3 dimensions, you will see that if you have a cube, yeah, then it can be decomposed into 3 factorial such convex hulls, all of the same volume, they fit inside a cube. Okay, I'll let you think about how that happens. So in n dimensions, the number of such convex hulls that fit inside the n-dimensional cube is n factorial, and they all have the same volume. Okay, so basically, this determinant computes the volume of some parallelepiped, and we need 1 over n factorial of that. When you have these n plus 1 points, this was the point x0, this was the point x1, this was the point x2. So what you should actually have been computing the 2 cross 2 determinant involving x1 minus x0, x2 minus x0, this vector, and x1 minus x0. Okay. Now, if you see, if you did one step of our usual determinant manipulation, that is, you subtract the first column from the second column, the vectors that you will get here, so this 0 will go away, yeah, and basically you will get x1 minus x0, xn minus x0. So those will be the values, vectors that will arise here, and the first column would, the first row would have been cleared up. So when you compute the determinant, you are actually computing the determinant of this, where each xi has been replaced by the corresponding vector. That will be the volume of the parallelepiped. But that parallelepiped contains n factorial such objects, so it is 1 over n factorial. There are other ways of thinking about this. So this is true. Now, it turns out that a small calculation shows you that when you, let me just, I made this little animation, so please allow me to. So when you fit this smallest ellipsoid here, yeah, it fits like this, and it has a center. Yeah, let us say that center was minus x here. Yeah. So you can find out what this minus x should be. Okay, let's assume that the ellipsoid sits in this position. What should be minus x? And then compute the volume of this ellipsoid, and it will turn out that the ratio of the volumes is this e to the power this, which was our claim. But I'll stop here. Questions? Yes, where were the claims? My claims have vanished. And if you prove these 2 claims, you're done. This claim was relatively easy. You can check. This claim needs a little bit of work. We will do it next time. But this is not all. This is just the beginning. Okay, these are rough ideas for ellipsoid method. The hard work will be when we start trying to. So when we do this ellipsoid method, it turns out that we will need to take some square root at some point. And then annoying people will ask us, how are you sure that your square root is correct? Because you're going to represent it only in finite number of bits. And when you represent square roots and such numbers in finite number of bits, what sort of errors come in when you compute these ellipsoids? Do they make a difference? And we will have to keep everything under control to say that you will eventually land up inside the point. Questions? Please read the book. The book has an informal description. What we will be discussing in class will be slightly more formal than what is there in the book. Okay, I am again using Shriver's book for this part of the our discussion. Questions? Okay, so let's stop here. Thank you very much. And the homework was put out. Please start working on it immediately. And if you have any questions, ask.
Thanks, Vivek.
Thanks. Bye-bye.
Thank you, sir. Bye.
Thank you. Thank you. So, Shomajit, are you there? Okay, I'm closing it nevertheless. Shomajit, you are still there.